there's an important quantity about at least square matrices that we care a lot about. And this quantity is called the determinant. The determinant allows us to understand whether or not a matrix has an inverse or not. Remember that if we have a matrix A, we say that it has an inverse, A inverse, if when we multiply them, we get an identity matrix. And this only holds true for square matrices, that is, n by n matrices. The way that we can determine if a matrix even has an inverse, because not all matrices have inverses, the way that we can determine if one does have an inverse is if the determinant of a matrix is not equal to 0. If it is equal to 0, then we say that the matrix is singular. Now, what is this determinant? Well, it's fairly challenging to explain, but there's kind of two ways to go about it. I explained it through one way in the notes, and I think I gave a fair enough detailed description of that approach, and I think you should read through it, because that's, in my opinion, the more proper way to define a determinant. But the way that I'm going to do it here in the videos is the way that a lot of textbooks and online outlets tend to define the determinant. So if we have a simple 4x4 matrix, I'm sorry, 2x2 matrix, then the determinant of this matrix is the quantity of A times D minus C times B. Okay, that's it. That's very easy. Now, things get more complicated when we have matrices of larger sizes. In this case, this is broken down by the following. We basically pick a row, and the convenient way is picking the row with the most zeros. That's the most convenient way to compute the derivative. I'm sorry, the determinant. And here's what we do. We take let's say we pick the first row. We pick the first element. We remove the column and row elements from that, based on that element, and we take the the determinant of the corresponding sub-matrix. So here we have A, so we remove this and this, and we're left with A times the determinant of the matrix E, F, H, I. This means take the determinant of. Okay, so another way of, if I have a matrix A, writing this is the same thing as saying the determinant of A. Okay. Now, here's the weird part. We're going to alternate the signs. We always start with plus here, and then do the same thing. We have B, remove this and this, which gives us the equation B and the determinant of D, F, G, I. And then we add this number, C, times the determinant of this matrix. Why? Because we remove this and this. So determinant of B, E, G, and H. And this just follows the equation that we did here. This times this minus that times that, so on and so forth. So let's do an example. Suppose that we have the matrix A, and we have 1, 5, 0, 6, 7, 0, 8, 1, 4. Well, we could go about taking the determinant as we mentioned up here with the first row. But remember what I said. You want to pick a row that has the most zeros, or a column, whichever. In this case, we have 2 zeros here, and that makes it easy. It makes it easy because we have 0 times the determinant of this, which is just 0, and 0 times the determinant of this, which is just 0. Which means the only determinant we need to find is this submatrix here, and multiply that by 4. However, we need to be careful. Start with plus, minus, plus. So we're going to do plus this times determinant of this, which is 0, minus, and then plus. So this is just simply equal to 4 times the determinant of 1, 5, 6, 7, which is just 4 times 1 times 7, minus 6 times 5. Just want to make sure I have the signs correct. One second. So, as you can see, 0 times that, 0 times that, 4 times this, which we get plus, minus, plus, minus, plus, plus, minus, plus, minus, plus. Okay, so it's still, we're still good. Which means we have 4 times 7 minus 30, which is minus just double checking my math here. Hold on. Yeah. Yes, sorry. Just making sure that we can be allowed, make sure I did not screw my math up here. But yeah, as I just recalled, of course, we can have negative determinants, which become very important when we get to multivariable calculus. But anyway, 7 minus 30 is, of course, minus 23, which then, of course, we have minus, I believe that is 90, what is that, 92? 4 times 20 is 80. 4 times 3 is 12. Yeah, 92, minus 92. So that's how we compute the determinant of a matrix. We pick the row or column, but we have to abide by this plus or minus scheme. So let me give you another example. Suppose that we were trying to find the determinant of 0, 1, 0, 3, 4, 6, 2, 1, 0. We can take two approaches here. We can pick this row to use, or we can pick, this column to use, or this row, and it doesn't matter which one. However, notice that we have this plus minus plus scheme, which means that we're going to add a minus or a plus sign on the front of the term we use. So notice we have 0 here, and that wipes out whatever this is, 0 here. And what we're left with is trying to find the determinant of the matrix formed by those numbers. So the determinant is actually minus 1, okay, plus minus 1 times the determinant of the 3, 2, 6, 0. And that boils down to minus 1. 3 times 0 is 0, minus 6 times 2 is 12. So we're left with 12. Let's check our work, though, because we should get the same result doing minus, but using this as the column. So we remove this and this, and to get the determinant of this, but it's multiplied by 0. We don't care about that. Likewise for here, but here is non-zero, so we have to find the determinant of the matrix formed by these quantities. So we're going to get minus 6 times the determinant of 0, 1 and 2, 1. 1 times 0 is 0, and 2 times 1 is minus 2, because we do this minus that, and we get minus 2. And of course, that gives us the same result, which is 12. What if we have matrices bigger than 3? By the way, that's not always going to be the case. Suppose we have 1, 1, 0, 2, 3, 4, 1, 1, 1. What do we do then? Well, I'm going to pick, remember, the one with the most zeros, and I'm going to use 1 because 1's a little bit easier. This is just equal to 1 times determinant of this minus 1 times determinant of, nope, 1 times determinant of that matrix times 0 times determinant of this, but I don't care about 0 because 0 goes away. So this is 1 times determinant of 3, 4, 1, 1 minus 1 times determinant of 2, 1, 4, 1. And then we have 0 times whatever. 3 minus 4 is minus 1 minus 1 times whatever this. 2 minus 4 is minus 2, which of course we get just 1. So there you have it. That's the determinant of that. What about bigger matrices? What if we had 4 by 4? I'm going to use a very easy example to illustrate because I don't like large matrices, but here's what we do. We do the same approach. Here we have all the same numbers, so it doesn't really matter, but here's what we do. We pick one, we pick a row or a column to use. I'm going to pick the first row. And we do 1 times the the determinant of this matrix, meaning this one. We then subtract that with 1 times the determinant of this matrix, okay, which of course is 1, 1, 1, 1, 1, 1, 1, 1, 1. We go back to plus, right? Plus, minus, plus 1 times determinant of that matrix, right? So we have 1 times determinant 1, 1, 1, 1, 1, 1, 1, 1, 1. Minus, we have another minus, right? Minus here. 1 times determinant of everything not in these. So this matrix right here. 1, 1, 1, 1, 1, 1, 1, 1, 1. Now there's a neat little trick here. Obviously you can see that this goes to 0, this goes to 0. We're going to get 0. That's not always the case, not always as easy. But how do you then find this out? Well, you need to find the determinant of this matrix, which is the same thing we did before, right? We pick a column or a row with the most zeros, if there are any, and then we do this times the determinant of that minus this times the determinant of this, and so on and so forth. So this is a recursive way of defining the determinant. I don't particularly like this way. I like the permutation approach that I take in the notes. However, the choice is completely up to you, whichever you feel is more simplistic to understand. So anyway, I'm not going to ask you to solve crazy determinants. I'm just not. It's too much. But with that stated, I think that you should at least understand both approaches to the determinants. What does a determinant represent, by the way? Geometrically, it represents the volume of a shape that's formed by the vectors in our matrix here. But I don't really want to get deep into that because that's going too far outside of the scope of our discussion here. The only thing you need to understand about a determinant is that it represents a property about the matrix itself. And you need to understand, with some mild understanding, of how to compute it. Frankly, in our next lecture, you're going to find that we're just going to run the matrix through Python, and Python's going to just give us back out the results of that anyway. So life is good on that front.